This is a problem that involves both kinematics and conservation of momentum. So we'll first do the kinematics to find out exactly where this rocket is when it explodes, and then how fast one of the pieces must be going given how high it rises. So we'll start with the kinematics. And using simply the acceleration, which is upward at 10 meters per second, assuming it starts at rest, it doesn't say that, but you assume on the ground it starts at rest, and the time that it rises is 2 seconds. So here's the rocket on the ground, not moving. And now it's accelerating up because it's exhausting its gases and has a force, a thrust force up. So it's going to rise, go faster and faster and faster. We need to know how fast is it going after 2 seconds. So the kinematics that we can use is just Vf is Vi plus At. So the initial velocity is 0, acceleration is 10, and the time is 2. And so it must be moving up at 20 meters per second after 2 seconds. We're also going to need to know how high it is off the ground at that point, because we're told how high it rises eventually. So its position vertically off the ground, we can just use y is VIT plus 1/2 AT squared to see that it is half of 10 times 2 squared, and it's in fact 20 meters above ground. So that's part one. Now the rocket explodes and breaks into 2 pieces. It says that one is twice as massive as the other, and since the mass is 1,500 kilograms, one obviously must be 1,000 kilograms, the other 500. But that doesn't really matter now that we're just worrying about kinematics. So let's carry on this problem. Part 2 is more kinematics, but now we're just looking at the lighter piece traveling up from that position of 20 meters off the ground. So here we have the rocket, and we want to know after the explosion. So this is kinematics after the explosion. It's gotten a huge kick from that explosion, so it's going to be going much faster than that 20 meters per second. And we want to know just how fast is it going after the explosion, such that it's going to rise 530 meters off the ground. Now it's already 20 meters off the ground when it explodes, so that's the 20. 530 is up to here, and so really the only distance we're worried about is this 510. And at the top of its flight, its final velocity must be 0. So the question is, how fast was it going after that explosion in order to rise an additional 510 meters before stopping? So we can use kinematics. Vf squared is Vi squared plus 2ay, and solving that for Vi squared, we get negative 2ay. So it's negative 2 times negative 9.8. Now it's just in free fall. So after the explosion, there is no more thrust from its gases or however it was moving up. It's simply in free fall. And it rises an additional 510 meters. And so that gives us an initial velocity after the explosion of 100 meters per second. Much faster than the 20. Okay, now we're going to use conservation of momentum to figure out how fast the smaller piece shot down after that explosion. So this is now conservation of momentum. And we'll do a before and after. So before, we have the whole rocket, the 1,500 kilograms, moving up at 20 meters per second. We don't care how high off the ground it is, that's irrelevant. And then after, it breaks into 2 pieces, one of which is traveling up at 100 meters per second. And that's the smaller piece, so that's the 500 kilogram one. And then the larger chunk obviously has to travel down at some speed. That's what we're trying to find. And its mass would be 1,000 kilograms. So conservation of momentum. Momentum before is 1,500 times 20 must equal momentum after. 500 kilograms moving up to 100 plus 1,000 kilograms. You don't have to put a negative in. It's going to come out negative all by itself, times that final velocity of that larger piece. And if you solve, you find that that velocity indeed is negative 20 meters per second. So the negative tells you it's going down, and the final answer is that the smaller piece moves down at 20 meters per second.